All right, welcome everybody. We are scheduled to get started in just a minute here. I see we've already got 11 viewers online, so that's great. As always, I'll be taking questions in the chat. So just below your video on YouTube, there should be a chat window. You're welcome to pose questions to me, to your classmates there. If you'd prefer to pose a question anonymously, I've also got my JU email open on a separate tab. I will be making sure to check that throughout this afternoon's stream. Just to confirm why we are here, this is an online class for Jacksonville University's Physics 151, General Physics Mechanics. We are going to do our sort of last formal lesson this week, and then kind of going into next week, we'll talk a little bit more about how the semester wraps up with the final project, and I'll be happy to go back over any topics that anybody needs, just like we would in class. Before we get into the physics for today, I do want to confirm that JU will be finishing its spring semester online, so we will not be returning to campus for the end of this class. I will miss seeing y'all and miss getting to see your presentations in person, but I have confidence that everybody can finish this class well and get something out of it. If you are taking summer classes at JU, do keep an eye out for when the return to campus is authorized. The last notice I saw was that we would be off campus until June 20th. And so the current plan is for summer classes to start online. If you know who your instructor is for a summer class, it would not hurt to go ahead and email them, try to find out, what they are expecting of you. See if you need to get any, technology or anything set up wherever you are. I hope you are all safe and isolated and healthy. What we're going to look at today is gravity in space. You can, I believe, see that. Yeah, you can see that on the streaming window there. Let me go ahead and get you the link to this whiteboard. I'm going to paste that into the chat. Whiteboard. There we go. And then I'll also get you the link to our trinket page for today, for this week. Most everything I say today is going to be covered in the trinket page. So if you watch this video and go over the stuff in trinket, you should be pretty well covered in terms of understanding what's going on. I also wanted to give you a reminder to please sign up for final project topics and groups. I currently only have 7 names down in the topics and a couple of names down in the groups. It is optional if you want to do the final project in a group or individually. And so if you're just looking for an easy way to connect with people who are interested in the same topic you are, just go onto the groups page. I have emailed those links to you. I won't put those in the chat because those contain your personal identifying information. So that way we can keep those anonymous. So anyway, I have emailed those to you. I will email those to you again after this stream ends, along with a link to an archive of this video in case folks need to watch it after the fact. Okay, so with that out of the way, I want to talk this week about gravity in space. So you have worked with gravity before in this nice, simple approximation of this constant force that we call the weight, right? So far, if you want to talk about the force of gravity on something, we've approximated that as the thing's mass times this thing little g. And if you had a high school physics class, you probably learned this g as the acceleration due to gravity. That's really kind of an unfortunate name that it has picked up. What it really is the gravitational field of the Earth, right? And you say, okay, well, it works out being the same thing. Well, not really, because what this gravitational field has a few factors to it. It has a capital G. This capital G is a constant throughout the entire universe. It is 6.67 times 10 to the minus 11 newtons meter squared per kilogram squared. You are not expected to memorize that. Literally, you go to Google and you ask Google gravitational constant, and it will spit out the number for you. 6.67 times 10 to the negative 11. And I'm pretty sure the rest of that works out to the units that I've spat out. And so when you're doing math with this, you never actually have to write that. You can just say gravitational constant times mass of Earth times mass of Sun divided by distance between Sun and Earth squared. And you can actually use this to calculate the force between the Sun and the Earth, except I don't think it knows what distance between the Sun and the Earth is, so we're going to look that up. Distance between Earth and Sun, there we go, 92 million miles. Okay, so we'll put this into, I know it knows the rest of these things, 92 million miles. So like you can put words like this into Google, and it will do it usually does the math for you. There we go. Okay, I had mass of Earth capitalized. Goodness, Google. You would think Google would be a little less sensitive than that. 3.6 times 10 to the 22 newtons. That's the gravitational force between the Earth and the Sun, because we just used the gravitational force equation here. Anyway, that's a little bit of a side tangent. Sorry. Let's show you what this letter is. A lot of students, and I mean a surprising number of students, confuse capital G with lowercase g. So I'm just going to say up front, they are not the same thing. This is the local gravitational field near the surface of the Earth. This is 9.8, like you've been working with before. This is the universal gravitational constant that is the same throughout the universe. This is 6.67 times 10 to the minus 11. They are not the same number, so just keep them separated in your mind. So anyway, the way you calculate the gravitational field anywhere, not just near the surface of the Earth, you take capital G, you multiply by the mass of the thing that's in the center. So in this case, that's going to be the Earth. So let's suppose we've got the Earth, And let's suppose we've got, let's see, anonymous quagga joined. I don't know what a quagga is, but let's say you've got a quagga floating in space out here. So in this case, this M, this is going to be the mass of the quagga out here in space. And this E is going to be the mass of the Earth here. You divide that by the distance between the two squared. Now I know R usually means radius. In this case, it is not a radius. R is just the distance between the two. So this is the distance between the quagga and the Earth. And so what you do, you grab the center point here, you grab the center point here, you look at the distance between those two centers, that is the distance here. So let me show you how you might use this, for example. Let's take our gravitational constant thing here. Let's take the mass of the Earth. What you notice is we're going to take out the mass of the other thing here, and we're going to divide by the radius of the Earth. Because basically, you and I, we live here at the surface of the Earth. So this is at little r equals the radius of the Earth. So we're going to put in the gravitational constant. We're going to put in the mass of the Earth. We're going to put in the radius of the Earth. We're going to press enter on this. Lo and behold, you get 9.8 meters per second squared. So little g and big G are related, right? Because the way you get little g is from taking the gravitational constant, capital G, the mass of the Earth, divided by the radius of the Earth squared. That gets you the acceleration due to gravity near the surface of the Earth. So what we're doing when we use this F equals mg thing, we're saying that we're going to assume that this little g here, we're assuming that that is basically constant, right? Because if I climb from the first floor of a building to the second floor of a building, I'm only going up 10 meters, right? So if I go from, say, the first floor up to the second floor, I'm going up, let's say, 10 meters. Compare that to the radius of the Earth, right? Let's compare that to the radius of the Earth. 6,000 kilometers, 6.4 million meters. When you go up 10 meters compared to 6.4 million meters, guess what? You haven't really gone up that far. And so when I go from the first floor of a building to the second floor of a building, this value of G really doesn't change that much because this value of R really doesn't change that much. It's not so when our quagga goes up into space, right? It's not so when we go into orbit. So when we're putting a satellite in orbit, we're trying to, launch a spacecraft, then we have to think about this thing changing. So this F equals mg, this is fine when we're near the surface of the Earth, or really the surface of any planet. But when we get out in space, we have to change this. Now, I mentioned you can use this for any planet, right? So, like, for example, I could replace Earth here with Mars. Right? I could say mass of Mars and radius of Mars. And I'll get the gravitational field on Mars. It's about a third of ours. I guess it's closer to 40% of ours. Somewhere between 30 and 40% of ours, right? Because it's 3.7 meters per second squared, right? So if you go on Mars, you weigh about 40% as much as you do on Earth. I can do the same thing with the moon. I can put in the mass of the moon and the radius of the moon. So when I'm walking on the moon, I've got an acceleration due to gravity of 1.6 meters per second squared. It's about a sixth of our acceleration due to gravity here on Earth. So you can do this with any surface, with any body in the universe. You can even, if you wanted to, use the sun. I don't recommend walking on the sun, but let's pretend you wanted to design a spacecraft or something. There you've got a gravitational field of 274 meters per second squared. So on Earth, ours is about 10. So this is 27 times the gravitational field of the Earth. Same thing you can do with Jupiter. We'll do radius of Jupiter. This will be our last one, I promise. That one's 24 meters per second squared. So it is about twice what ours is. Now, again, that's on the surface. That's on the edge of the planet. If you go into Jupiter's clouds, then you start getting the atmospheric pressure, and that's what will kill you in Jupiter. So in Jupiter, it's not the gravity that kills you. It's the atmospheric pressure. Okay, so that's a little bit of fun that you can have with that. But what I want to talk about is how we turn this into a force, because I need to be able to combine this form for the gravitational field with this form for the weight. In order to do that, what we're going to do is use the full-fledged force of gravity. So again, here's my object in the center. Again, let's have that be the Earth. And let's suppose we've got a satellite out here. The way I get the force that's acting on the satellite is with a few pieces. First, I put in my universal gravitation constant like I had before. Then I take both the masses of these things. So I take the mass of the satellite times the mass of the Earth. And again, this can be any two bodies. This could be the Earth and the Sun. This could be a satellite and the Earth. This could be a rocket ship and the Moon. And then I just divide by the distance between the two. So that's this center to center line distance r here. Now, this needs to be a force, right? Forces must be vectors, right? So I need to somehow encode this thing so that the gravitational force always points from the satellite to the Earth, right? I can't ever have repulsive gravity. If you ever find repulsive gravity, let me know. I'll help you write up the paper and we'll share the Nobel Prize, right? So what I need is to be able to turn this into a vector. That's where handy things called unit vectors comes in. Now, we talked a little bit about this before. A unit vector is a special kind of vector that has a magnitude of 1. So we're going to have a vector called r hat. It's special in that it has a magnitude equal to 1. It's going to go from the central object to the outer object. So in other words, you can think of this distance here as being a distance vector r. And this r hat is just the unit vector of this vector here. So if I want this thing to point from the satellite to the Earth, I need to multiply this whole thing by r hat and then put a minus sign in front. The minus sign just means it's going to point inward, right? So I'll have a negative r hat. So the negative is the thing that makes the force of gravity attractive. If you could ever find a way to turn that minus sign off, if you could ever find a way to turn this into a plus sign, you would have anti-gravity. You would have gravitational repulsion. We haven't found that yet. We're pretty sure it doesn't exist, but you know what? I would be happy to be wrong about that. This is going to come up next semester when you take PHYS 152, because the force between two charged objects follows the exact same pattern. You have a constant, you have the two charges, you divide by the distance squared, you multiply by the unit vector. The only difference is, because you have positive and negative charges, this force can be attractive or repulsive. So think of this also as an introduction to electric force as well. Okay, I want to give folks, we've been doing this for about 13 minutes here, so I want to give folks an opportunity to ask questions in the chat or over email. So I'm going to take a short 60-second hydration break, and you let me know if you have any questions so far. It's also worth reminding you, probably while you're typing questions, it's also worth reminding you VPython can calculate unit vectors for you. So this thing, we leave this up to VPython to do, right? You will learn how to calculate unit vectors in grave detail in Calc 3, but for our purposes, it's a thing that VPython gives you. And I see folks are already emailing me their participation documentation for the live stream. Thank you so much for doing that. Don't forget to submit your documentation for being here. Just a quick screen grab or leave a comment, and you can make sure you get that credit that you deserve. All right, I haven't seen any questions coming in. Feel free to continue sending in questions as you see the need. What I'm going to do now is show you your activity for this week. So we're talking about gravitational force in space, right? Joel posed a question. R hat, the distance between the distant satellite. So Joel, what you want to do is you want to distinguish between R, which is the distance, and r hat, which is the direction. So r is going to equal distance, r hat is going to equal the direction. Right, so you think about vectors having magnitude and direction. What we're separating is the magnitude and the direction. So you can also think of it as, for example, being the angle between the two. It's a little bit more complicated than that because it has to be a vector. But it's basically going to be three numbers that point you in the right direction. Okay, what I'm going to do now is show you your activity for this week. What I want to show you is the video that you're going to use, because this is gravity in space. I don't really expect you to get a video of stuff flying around in space. That's a little bit beyond our capabilities. Even when we're meeting in person, you certainly aren't going to be able to do that, while we are self-isolating. So what I'm going to do is I'm going to show you the video that you're going to use. Everybody's going to have the same video. I have a link for this in the trinket. What you are seeing here are stars. Each one of these little bright spots is a star near the center of our galaxy. And I want you to see what's happening to these stars near the center of the galaxy. Now we're going to zoom in. We're going to zoom in and see what's happening with these stars. Again, each one of these is a star, and we're tracking their trajectory. So this is doing the tracker for you. See how this star whips around in this ellipse? Let's take a look at that again. Yeah, so follow this star right here. You notice it flings itself around. So it's going around in an ellipse, and it gets faster when it gets to this point and then slower when it gets farther away. That's evidence of something acting on this thing with a gravitational force. Now I'm up to the ads. I don't want those. All right, so let's just pause this near the end. There we go. So you saw it whip around at this point. It's going slower over here, faster over here. It's moving in an ellipse. So there must be something pulling this thing around, right? Because in order for me to have a gravitational force, in order for me to orbit around something, I've got to have a gravitational force. When I look in the middle here, I don't see anything. So let's have you in the chat tell me what you think there is inside this space here that is both massive enough to pull a star around and that would not be visible. Is there anything you can think of in space that might be massive enough to pull a star around in an ellipse and that you wouldn't be able to see in space? Let me know in the chat. All right, I'm pretty sure there's only one option that's going to come to mind. And sure enough, people have chosen that. So I've got a lot of folks suggesting that this must be a black hole. A few of you are even using some fancy vocabulary and saying it's a supermassive black hole. Yes, so this is near the center of our galaxy, right? So we are in the Milky Way Galaxy. These are stars in a cluster near the center of our galaxy, and they are flying around here, right? I mean, this is obviously sped up. You can see the years up here. But this thing is flinging around here. This is right where we are pretty confident that there is a black hole at the center of our galaxy. We're pretty confident there's a black hole at the center of every galaxy. And so astronomers work and astrophysicists work very hard to study the black hole at the center of our galaxy. So somewhere over here, there is a supermassive black hole. Supermassive just means it's much, much, much more massive than the sun. I could be wrong about this, but I think it's so massive it has to have been formed during a black hole merger. I could be wrong about that, but I'm pretty sure we're confident it formed during a merger of one or more black holes. So what you're seeing here is a star orbiting around a black hole. And I think it's pretty cool, right? Because usually we think of stars as being these supermassive things. We tend to think of our sun as being pretty stationary, but our stars are not, right? I mean, this thing is whipping around here. And you also probably guessed it from the title that keeps popping up here. So think of this as your tracker video for the week, right? So this observatory has already done the tracking part for you, where this is the trajectory. Your goal is going to be to use our simulation for this week, our VPython code, to get this thing to whip around here. Now I'm going to play this again. What I want you to do is tell me, what are some measurable values we could use to compare this video with our simulation? What are some measurements that you could take off of this screen, off of this video, in order to compare with our code? Again, I'll play it again. You show me what we might be able to compare. I'm actually going to turn the playback speed down to half just so you can watch a little bit better. So what are some numbers on here we could use to compare? All right, Cody has suggested time. Where is there a measurement of time in this video? Okay, Andre is suggesting velocity. I don't see any velocity listed on here. Oh, we've got a distance. Courtney's suggesting distance. So you notice we've got a distance marker over here of 10 light days, right? This is so big, we have to measure it in light days, right? So this distance marker up here, this is how far light travels in 10 days. And I've got Brady and Cody suggesting that we've got a year up here in the upper left. So you have distance and you have time, right? So if you look up here, you've got the year labeled. So we've got starting at 1992. Please do not tell me what you were doing in 1992. I don't need to know. You need to be reminded of how much older I am than my students. So we start at 1992. We go forward, and we keep going along, keep going along. So one complete revolution goes from 1992 up to about 2007, 2006.9. So this whole thing takes 15 years. This whole orbit takes 15 years in order to complete. And it's got a distance. Let's see, this is about 10 light days. You can't see me putting my finger up to the screen, but this entire distance from the top to the bottom is about 10 light days. So 10 light days, top to bottom. Right? Which is pretty cool, right? So it's very clever of you to look at the year and look at the day and look at the distance. Basically, from that, we can use that to compare with our tracker. With our VPython. This is doing the tracking for us. So this is the 1 week you don't need any tracker. We had a week without any coding. Now you have a week without tracker. I'll give you a link to the black hole video. There we go. Excuse me. I've also got that linked here on Trinket. So let's take a look at how we're going to simulate this in the code. So on Trinket, there's a page here to remind you about how gravitational force works. I encourage you to read that. Let me get that out to you again, just in case we have folks recently joining us. There we go. Then it's got the link here to the black hole video, so you can study this. You can get this as accurate as you want. But basically, we're looking for an orbit of, 15 years, and a height of the ellipse of 10 light days. Excuse me. Then we're going to come along to the code. Here is where we've got the code. Let's see. Could you use the time and distance by the velocity to compare as suggested? Let's see. That would give you average speed, yes, but not the velocity at any particular moment. There we go. So what I've got here is a simulation. Let me get this to full screen, and I'll bump up the font size. So here we've got a simulation. Mark on red. There we go. Here we've got a VPython code that is recreating this this motion, right? So we have our star here in yellow. I've got the black hole here at the center. I made it gray so that you could actually see it. And so then I've got the distance marker of 10 light days. So I set this to scale here. And what we've got is pretty standard setup that you're accustomed to by now. We create a star and we create a black hole. Right? They've got all the necessary information you need. We've got the starting position, we've got the starting velocities, we've got their masses, we've got their color. Not that that really matters for the physics, but if you wanted to truly make this a black hole, you could change it black if you wanted to, turn it invisible, who knows? Then I've got a little bar set for the scale. That scale is just there to kind of mimic our video. Then we've got our animation loop. You know what an animation loop looks like right now. We've got the condition for stopping. So this piece right here is just a fancy way of saying while you're doing one revolution, right? There's 2 pi in one revolution. So we're saying while theta is less than 2 pi. And then we go through the usual Euler-Kromer method. So you have seen this done about 7 or 8 times now. First, we calculate the force. This is really the only thing that is any different. We calculate the force on the black hole. We calculate the force on the star. The way we're going to do that is this g-force function here. So you might remember we've got our full-fledged gravitational force equation. Let me pop this out so that we can see that. Go back to full screen. There we go. So we need to have all of these pieces together. This actually takes a few steps. So I've gone ahead and swept that into a function here that we're going to define. So down here we've got g-force defined. This is the thing that calculates the gravitational force on object 1 from object 2. So you notice, for example, I'm calculating two forces here. I'm calculating the force on the black hole and the force on the star. Now, we know from Newton's third law, those have to be equal in magnitude but opposite in direction. So that's why we have to swap the order here. So this one's got g-force of black hole, comma, star. This one's got g-force of star, comma, black hole. Right? So that I can swap which one is giving the force and which one is receiving the force. So down here, we've got our g, our universal gravitation constant, 6.67 times 10 to the minus 11. Down here, we calculate the distance vector from object 2 to object 1. So this might help clear up the difference between r and r hat. This is the distance vector, so you're going from the one that's exerting the force to the one that is receiving the force. Step 3, we calculate the force magnitude. So we've got our gravitational constant times mass 1 times mass 2. Then we divide by the magnitude of the distance squared. This is just the magnitude down in the denominator, right? I can't divide by a vector, so I've got magnitude of the distance squared. Then we turn our force into a vector. So remember, vectors have magnitude and they have direction. So this piece brings in the magnitude, g m1 m2 over r squared. This piece brings in the direction, the hat of the distance, right? So hat is VPython's function for a unit vector. So whenever you need a unit vector, you just use the hat function, plug in the vector, and it will give you the unit vector. So this is the piece that is hiding the vector math for us. And then we're just going to return the force vector. I do see some questions coming in. Let me wrap this up and then we'll answer some questions there. So we're going to return that vector. And so we got our force. And now we just have to update everything like we did before. So we're going to update the velocities, right? So velocity gets updated by force times dt over mass. I don't know why this thing keeps jumping like that. That's getting annoying. We've got the force times the time step divided by the mass. That's our update for velocity. And then we've got our update of position. That's going to be the velocity times the time step. And you notice I'm doing that for both the star and the black hole. So we are technically updating both of their positions and velocities. When I run this, that brings my star whipping around the black hole. You notice the black hole hardly moves because it is so much more massive than the star. It doesn't really appear to move, right? They're experiencing the same force. They just get a different acceleration. And so we whip around here as an ellipse. And basically, every time you have the gravitational force, you're either going to have an ellipse if you have a bound orbit, or you're going to get a hyperbola if you're going at or above the escape velocity. And so when I look at this, I've asked it to tell me what the period is. So it's going to print the period in years. Remember, your goal is to get a period of 15 years. And yet this is giving me 7.5 years, right? So you have to make a few adjustments to this thing. So I'll let you think about what you might be adjusting. Let's look at some comments. Courtney asks, could you use the time and distance to find the full velocity? Yes, that would give you the average speed. If you wanted the average speed of this thing, you could take that distance divided by the velocity. That's not really a thing we measure, so it's not really a thing we're terribly interested in. Cody asks, can you add multiple objects into the function? So let's say, for example, I had a binary star system. By the way, if you have not read The Three-Body Problem, it is an excellent, excellent sci-fi book. It is available through the Jacksonville Public Library. So if you have Libby, their free ebook app, you can get it as an ebook or as an audiobook. Excellent, excellent sci-fi novel. Excellent physics in there. Anyway, getting back to this. If, like, let's say, for example, I had a binary star system. So let's say I had 2 stars and a planet. The way I would do that, I would just add on more g-forces. So, for example, I would add on g-force of, object 1, comma, object 3. And basically, for every pair of objects, you need another g-force because the gravitational force works in pairs, right? You would just add in another g-force function with the new pairs that you are adding. Let's see. Courtney's asking, does the g-force function need to be defined in the code before it is called? Usually that is the case. GlowScript is set up in such a way that it reads the entire code and it can define the function after it's been called, so it will go down and look for it. So that is usually the case. So I'm technically cheating a little bit here, but I put it down below here so that you can focus on the stuff that you need to worry about as opposed to the thing that you don't need to change. let's see here. Oh yeah, and then I've got some stuff here about energy graphs. If you would like to graph some energy stuff here, you can. You don't have to. The main thing that you are interested right now is getting this period and this distance to match. There's really no graphs to look at. There's really no, checking conservation of energy or anything like that. Really, the thing you're looking to get is for the size of the ellipse to match and for the period to match. I think I had this up when I was testing the code to make sure the energy was conserved or something like that. So you can make energy graphs or distance graphs if you want. The main thing you want is to make sure that the distance matches, which it currently doesn't, and that the period matches, which it currently doesn't. So let's go back over the force and see what it is we can adjust. So if I want this thing to have a different period, I've got to be able to change the gravitational force, right? I've got to be able to give them a different force. Well, let's take a look at stuff we can change. I cannot change G, right? That is the same everywhere in the universe. I'm not allowed to change that. I could technically change the mass of the black hole, right? I could technically change the mass of the star here. But here's the thing. I'm multiplying by the mass of the star in the g-force, and then I'm dividing by the mass of the star in the velocity. So those actually cancel out. So if you go on and change the mass of the star, that's actually not going to change anything because it cancels, right? On the other hand, I could change the mass of the black hole, right? If I make the black hole more massive, let's see what happens. Let's suppose we change this from 1e37 to 5e37. I don't think that's going to work, but let's say we want to make it more massive. Zoom! Notice it gets around a lot faster. Oops, I went in the wrong direction, right? So making it more massive actually decreased the period of oscillation because it's got a much stronger force. So you actually want to make the mass of the black hole a little bit weaker. The other two things that I can change the starting distance. So Gabe asked, how do you adjust the position properly? So this is the one number I would change, would be the initial Y position of the star. The black hole is starting out at 0, 0, 0, and the star is starting out directly above the black hole. So if you just change this, you'll change that initial distance. So let's say, for example, I double this. Let's suppose I make this a 3.0, and we'll run it here. All right, it's definitely taking me longer this time. I'm not too happy with the shape of the ellipse. It's a little bit too squished along the x-axis there. But let's see what kind of period we get. Okay, I'm back to just over 7 years. Okay. The other piece I can adjust is the initial velocity of the star. I would recommend just sticking with the x component, leaving the y component at 0. If you adjust the y component, if you adjust the y component, you're just going to end up flinging it up this way. You're just going to basically be rotating the ellipse. So like, for example, I could double this thing as well, right? I can make this 3.0. And on the one hand, that makes it travel faster. On the other hand, it makes it travel farther away. So we'll see whether that ends up making our orbit shorter or longer. A couple more questions coming in. What's the difference between gm over r squared and gmm over r squared? So Courtney, the difference between those two is the first one is the gravitational field. That's the same for everybody. And the second is the full-fledged gravitational force. So you get one from the other by just multiplying by the mass. Cool. Ooh, I ended up with 13 years. Ooh, so I'm onto something here. I'm getting closer in terms of the period, but this ellipse is way too broad right now, right? This is way too close to a circle, right? I want this thing to be much more, let me get, oh, it's hidden. I exited the video anyway. I want this thing to be much more squished. And of course, Courtney's pointing out that ellipses have foci or focal points. Basically, the thing you're orbiting around right here, this black hole is one of the focal points. So if you can find where the focal point is on the ellipse on the video, you can find exactly where the black hole is. So that's one way you can find a black hole. There's actually nothing at the other focal point. It's kind of spooky in that sense. So anyway, that is your goal in this week's activity, is to take this initial information, adjust the star's initial position, the star's initial velocity, and the black hole's mass, and adjust those three numbers until you get this orbit to match. You're looking for the size of the ellipse, both its height and its width, to match, and you're looking for its period to match. That's it. You don't have to do any tracker. It's already been done by the observatory for you. You don't really need to change anything about the force here, because this is the gravitational force. It's been the same for billions of years. And yeah, this thing will spit out the period for you, and you can use this little measuring stick to figure out what the width of your ellipse is. Let's see. Let me give y'all an opportunity to ask any questions you have about this week's activity. That is all I have on my notes. In your letter home, what I would like for you to do is use this as an opportunity to explain to your reader how we know that black holes exist, right? Because, oh, you can't see them. How do you know it's there? Well, because we watch the stars go around in an ellipse like this. So I'd like for you to explain to your reader how this proves that black holes exist and that we've got our own black hole in the center of the galaxy. Next week, what I will do is spend this time reviewing any outstanding questions. And then we'll also take a little bit of time to look over some sample presentations. Actually, we've got a little bit of time now. So depending on how questions go, we might open up a sample final presentation today and go back over it again next week. All right, let me check in for any questions. So Courtney asks, how do we use the measuring stick? So you got a couple options. The simplest option is to literally just, let me get back to full screen here. The simplest option is to literally just use this, hold up a ruler or a piece of string here and use this as a scale for measuring. You could also, in principle, move that around if you wanted to. So you could take scale here and move its position. But basically, it's there so that, this is 10 light days. I mean, you can literally, put up a pencil, put this at one end, put your finger at the other end, and then use that to measure the distance. It's not entirely not entirely technical there. Okay. Courtney asked a great question that I will pass around to the group. How do we know which end the black hole is at? So when I go back to the video, that's a really great question. How do I know which end the black hole is at in the ellipse? Let me see if I can get this video back up. Okay, so here it comes around the ellipse. Zoom. All right, so how do I know whether the black hole is at the top end or the bottom end? Y'all let me know in the comments what you think about that. We've got a guess from Gabe that's at the bottom. I think I said it was at the bottom. I put it at the bottom in the code. But how do we know it's at the bottom? How do we know that's the end it's at? Right, okay, so we got a couple answers here. It's going to accelerate faster when it's closer to the mass. Because of the way this gravitational force works, right, because it's 1 over r squared, the closer the two things are, the greater the force is going to be. The greater it's going to whip around, right? It's going to pick up more speed when it gets closer. It's going to pick up less speed when it gets farther away. This is also where, for example, you can think of this in terms of energy, right? So you can also think of the gravitational potential energy. I'm going to have a lower gravitational potential energy when I'm closer and a greater gravitational potential energy when I'm farther away. So in order to compensate, I've got to have greater kinetic energy when I'm closer and less kinetic energy when I'm farther away. All right, cool. So like I said, I'm happy to take questions about this, or we can take about 10 minutes and look at a sample presentation for your final project. Let me know in the comments which way you'd like us to go for the next few minutes. Hydration break. All right, I've got 3 votes so far for presentations and none for more black holes. So here's what I'll do. If you've got more questions about black holes, etc., just let me know in the comments. I think I dinged my volume button. Here we go. Okay, just let me know in the comments, and we'll send one to me in an email. All right, let me bring this up for you here. I'm going to go to my PHYS 151 folder. So I've got this in the class folder. If you are already there, you can have a look at this. Let me get you the link for this. Here's a sample presentation. What I'm going to do is just get a shareable link for that. And I'll paste that in here. Sample presentation, paste. we go. All right, so let's open up the sample presentation. This is actually a presentation carried out by a group from last semester. So this is actual student work. This is not me putting one together. This is actual student work. Again, the way we'll assess the final project is just through a presentation. I'm not going to require you to do a paper for it because, why, make things more difficult for us in this unprecedented time in human history. So I just want to take a look at this one. This is a project that this group did involving PHYS and their motion. So they titled it PHYS motion. You notice that they've got a nice specific title. They didn't call it motion. They didn't call it PHYS. They could make it a little bit more specific by saying PHYS motion under magnetic force. Basically, the more specific you can make your title, the better, because we need to know what it is you're going to be talking about. And if you literally call it physics final project, well, guess what? Everybody is going to have that title. You want your title to be different from everybody else's. You can also put your name or names down here. I've deleted that just to make this anonymous. And they're using a standard Google Slides background and format here, so you don't have to do any fancy formatting. You can just follow the formatting in the default presentation. Here they give you an outline. The outline should be the last slide that you write because you literally just take what you're going to talk about and make it an outline here. You need an outline slide because you need to tell people, give them an idea ahead of time of what you're going to be talking to them about. Otherwise, they don't know where it's going. They don't know what to look out for. This is a standard thing that people expect you to do in a presentation. A lot of students, I love my students, but a lot of them tend to think that outline slides are a thing that Dr. Lane wants you to do. No, it is a thing your future boss wants you to do. So you practice doing it now. And basically, it's just an overview of what you're going to talk about. It doesn't have to have anything technical. It doesn't have to have anything, world changing. It's literally just one line on here for each slide. Then they talk about their setup, and they've got a picture here of their pass cards. It's a screenshot from their tracker project. So they've got their pass cards with their fan carts and their opposing magnets here. And they just give us an idea of what they were doing here. Remember, the purpose of slides is for you to have an outline of what you're going to say and for us to have an idea of what you're going to say, right? This is not a script. This is not block text. This is literally just your talking points. It's a few words on each line to remind you of what you're going to be talking about, right? Then they continue on with their setup. They actually embedded in here their tracker video. So you can go on and, let me mute that, there we go. So you can go on and watch that. Embedding videos in Google Slides is incredibly easy. You just click on Insert Video, and if you have your video up on YouTube, you just put in the YouTube URL. Otherwise, you can save it to your Google Drive and place that in here. So that's really easy to do. That's a nice touch. It's not required. It's just one of those things that makes it really nice and engaging for the audience. Really, your goal in any scientific presentation, and I break this rule, I acknowledge I need to do better on this, but your goal in any scientific presentation is to have a visual on as many slides as you can. Every slide would be ideal to have a visual. If not, at least every other slide needs some kind of visual, because science is a visual endeavor. It's a thing that we that is easily depicted in visuals. Let's say then they talk about their tracker, and this is the part where they're not going to talk about too much that people haven't done throughout the semester. They're just kind of recapping of what they did in tracker. Here they give a screenshot of their tracker, and basically this is where they point to the graph and they say, here's what we're learning from the graph. The red car is accelerating in the positive direction, the blue car is accelerating in the negative direction. Then we have an interaction, and then their direction of acceleration changes, right? That's the main thing that they would be pulling off here would be the graph. We love graphs in scientific presentations because the graphs tell the story, right? Here they show their position graph because that's what they're about to compare with on their VPython code that they did. And so they're trying to set us up for the comparison in a minute. And here they just go over the track results. They just kind of recap. It's nice to give a recap, every couple of slides so that people can follow you pretty well. Here they showed us the results of their code. You don't need to include the code itself. Chances are if you paste in your code, we will not be able to read it. Just include a link so that if you want us to be able to see it, you can open it in a separate tab. And then you can show us the code running. If you really want to walk us through how the code works, you can. But mostly we're interested in the results, right? So this is their animation. They've got two carts that are being pushed forward by fans and repelled by magnets. And so what you're seeing in the curvy part is the fan pushing them forward. And what you're seeing in this pointy part is the magnetic force pushing them apart. It's actually really cool. This is really cool because you have basically a parabola up here and then you have almost a cusp down here. It's pretty cool. And so they wanted to compare that with their results from here up in Tracker. And you can see it matches pretty well. There's a little bit of a downward drift to both of these, but you've got the parabola and then you got the cusp. Right here you got the parabola and then you got the cusp, right? And this took them probably a week to do the actual activity, to get it set up and do a couple of trial runs and stuff like that. That's another thing to keep in mind when you're doing this final project. You do as many runs and as many revisions and iterations as you need to get the graphs that make sense, right? Nobody gets a scientific project right the first time. And I mean nobody, myself included. And so here they put up their comparisons. So they got a screenshot from Tracker. They got a screenshot from Tracker here, screenshot from VPython here. And they're showing us that, the shapes generally match. Again, this one's got a little bit of a downward curve. This one's got this. But, if they were to make this one lopsided, they would look exactly the same. Here they got a comparison of the velocities. There's a little bit of wiggly going on with the velocity, but you've come to expect that by now, right? And then they have a conclusion slide. And the conclusion slide is literally, here is the thing that we learned. And here is the tip that my PhD advisor gave me that I pass on to you. You need to end your presentation on a conclusion slide. It's very tempting to get to the end, turn off the monitor, turn off the projector, and say, does anybody have any questions? And you're basically rushing to get back to your seat. If you leave up your conclusion slide, then the people in the audience get to think more about your presentation and they can ask more intelligent questions. And more intelligent questions are actually easier to answer than questions that come from a blank mind. Because if you put up a blank screen, right, if I present this and I go to the end, and I put up let's say I exit it, and I exit the tab, and nothing is there anymore, then there's not really anything for the audience to think about. If you leave up your conclusions, the audience can actually be thinking while they are asking questions, and those are actually easier to answer, right? So don't put up a blank slide. Don't put up a slide that just says questions. Don't put up a slide that just says thank you. And please, please do not put up a slide that is full of references. Do you need citations in a presentation? Yes, just like you do in a paper. But what you do, you put them in the slide. So let's say, for example, that they wanted to cite what a Pascal is. What you do is you put in a little footnote here. You can take this thing and go to Format, Text, Superscript. And then in the bottom, you can put down, let's say I go all the way down to the bottom of the slide, www.pasco.com. Oops. Right. And that is how you leave a citation in a presentation. You put the citation on the slide itself. Because here's the thing. If you put a bunch of URLs at the end, if you put a bunch of citations on the last slide, I guarantee you no one is going to read that. Right? They're going to be all crammed together in size 10 font for all of 20 seconds. No one is going to read that. No one's going to sit down and say, ooh, I need to scribble down all those URLs they put up there. No, don't do it. Put the citation on the slide where you reference it. Don't put the citations on the end. Nobody wants to see that. I'm sorry if somebody told you to do that. It's not a thing that we do, I promise you. But anyway, if you leave your conclusion slide up at the end, then folks can be thinking about your presentation and they can give you feedback and give you questions. Sorry, I know that's a bit of a soapbox moment for me, but it's just, I just want presentations to end well. It's the end of the semester. I just want presentations to end well. Yeah. Okay, I'm going to get off my soapbox now. There's a sample presentation for you. I've given you the link there in the chat. And it's also available here in the final project folder where you can still sign up for topics and groups. So that brings us to about 10 minutes till 3. So I am scheduled to be here until 3 o'clock. I would be happy to entertain any more questions anybody's got over chat or over email. Otherwise, I want to thank you all for your time. I do hope you're healthy and safe and well. And as I said, if there's anything that I can do to help you through this into the semester, please let me know. Courtney's asked their rubric for the final project. I had one when I had a paper that was due. Now that I don't have the paper, basically, Courtney, what your presentation needs is background, methods, and results, and those are the three things I'm looking to tick off in check boxes. Is did you give me a background? Did you give me your methods? And did you give me results? And honestly, with folks scrabbling together to get stuff online and everything, I'm not really going to get terribly nitpicky beyond that. Tyreek is asking, can you explain a little more about the period? Well, a period is how long it takes for something to repeat. And so what we are looking at is for how long it takes for us to go one lap around the ellipse. I don't really have more of an explanation than that. Tyreek, if you've got a more specific question, I'd be happy to answer that as well. What are we doing with it when we get the value at the bottom? So your goal is, this is the period from the code. You want this to match the period from the tracking video. So this, we figured out, has a period of about 15 years, it looks like, because we start in 92. We end at 2007, so that's about 15 years. So we started in 92, we end at 2006.9. So if you really wanted to get accurate, you can make 14.9, but your goal, oops, go to the other page. Your goal is to get this period out to be 15 years and to get the length to match. So right now I've got it at a period of about, what was that, something like 13 years or something like that. And your... but the problem is now I've got the thing too broad. So even if I get the period right, I want to then get the dimensions right. I want to get the height and the width appropriate. Marcus is asking, how do we present the final project? What will happen is I'll send out a Google Hangouts link and you'll share your screen to present. I'll also send a survey for times people can be available. What will probably happen, it'll probably be a couple of sessions to accommodate people's schedules is what I'm thinking. So what we'll do, and I misspelled accommodate, I don't care. What will probably happen is we'll pick like 2 or 3 times and just have folks go whenever they are available during those 2 or 3 times, because I don't, we are off of a synchronous schedule. I don't expect to get all, how many of you are there? 22? 20? Yeah, I don't expect to get all 22 of you in a chat room at the same time, but I bet we can get it down to 2 or 3. We'll do that in Google Hangouts, where you can share your screen. There's literally a share screen button. So if you just have your presentation open like this, you just click share screen, click present, and then walk it through like you do with a regular presentation. It's actually not a bad skill to learn, would be how to give a webinar. I'm actually thinking about maybe we make that, a requirement somewhere in our curriculum, because, there are a lot of seminars and stuff delivered online, and that's actually a good skill to learn. All right, I got a comment from Courtney addressed Dr. Lane. I'm guessing she hit enter by accident, so I'll wait for her to send that one out. Please let me know if I'm missing any assignments up to this point. Yeah, Courtney, send me that query in an email. That's something we'll deal with over email. All right, we're coming up to a few minutes left. I see our viewer numbers are dropped about in half. So I'll take, last couple of questions. And again, I want to thank you all for your time. You'll have opportunity to chat with me again this Friday at noon. I will send out a Google Hangouts link for office hours. If you've got any questions leading up to that, please feel free to reach out to me over email. I can answer them there, or I can answer them during office hours. Courtney's asked about predicted final grade. Yes, I'm going to try to get maybe sometime next week do a grade update. Let's see what day is it? It's currently the 25th. Next Wednesday is the 1st. How about this? I will make it my goal by the end of the day on April 6th to get out a grade estimate. So I will open up my to-do list. I used to have a weekly to-do list. Now I just have a spring semester to-do list because the weeks, they kind of run together. So I'm going to do under teaching, I'm going to put by April 6th, send 151 grade updates. Oh, speaking of grades, don't forget to look into the university has sent out a policy that you can elect to change to receive, instead of a letter grade, receive satisfactory, unsatisfactory for a grade. They're doing that instead of pass fail, I guess, because pass fail, I don't know, it sounds so dramatic and final. I kind of like the sound of satisfactory, unsatisfactory better. I'm not sure whether you do that for individual classes or whether you do that for all your classes. I would guess it's individual, but I don't know. I need to actually look at what the policy is. Why don't I open it while I ramble? Let's see. So what happens is what happens with that satisfactory, unsatisfactory is I submit a letter grade, and if you have elected the satisfactory, unsatisfactory option, then the grades are automatically converted by the registrar's office. So I don't know whether you take the satisfactory, unsatisfactory option, unless you are someone who has only submitted half the letters home, or you haven't submitted any letters home. Like I said, I will be sending out those grade estimates, but because of all that's gone on this semester, I do not plan for this to be the semester I put a line in the sand and say this is the difference between a D- and a B or something, So I don't really expect folks to be too disappointed with that. But if you feel like you would be more comfortable taking the satisfactory, unsatisfactory option, please feel free to take advantage of that. So anyway, I submit letter grades as usual. Registrar converts them to SU. There's some detail about if you need a minimum grade course or course grade for a future class, so just be sure to look into that. S or U are not calculated in GPA. S does receive credit. Oh, excuse me. I was mistaken. I do find out whether you opted for a satisfactory or unsatisfactory grade. Okay, so that's for my information purposes, but I still submit a letter grade. It's still not clear to me whether that's class by class or for the entire semester. I'm guessing it's class by class. Yes, you can still do satisfactory, unsatisfactory, even if a minimum grade is required in the future. Let's see. In a course where a minimum grade is required, students will have to repeat the course minimum grade is not met. If SU is selected, SU will display on the transcript. The course will not show as satisfied. The student will have to, okay, it is saying that they would have to repeat. Excuse me. It's saying that you... So the official email from the university is saying that an S or U is not going to satisfy the future grade down the line. So you want to take that into account when you're deciding whether to take an S or a U. If it were me teaching the class and I'm not speaking for any other faculty, but if it were me teaching the class, I would probably handle that on a case-by-case basis, because we can override requirements to get into a class. So I would probably handle that on a case-by-case basis myself. No, you don't need a B to take PHYS 152. Did we put a C in that? I don't remember. Let me look up the catalog really quickly. This will be the last thing I look up, and then I need to go get second lunch. Let's see. We're going to look at PDF for the catalog. Let me just pull up that course requirement really quick. PHYS 152. We're going to go reverse here. Here we are. Okay. Yes, so PHYS 152 does require a C or better in PHYS 151. PHYS 152 does require a C or better in PHYS 151. If you take the SU option, I can encourage the instructor to take that on a case-by-case basis. Let me spell check encourage. There we go. So yes, it requires C or better. If you take the SU option, I can encourage the instructor to take that on a case-by-case basis. Actually, when is the SU option choice due? I will do this offline. I'll find out when students are supposed to select the SU option, and I'll make sure I get my my grade estimates out before then. All right, so thank you all so much for your time. I'm going to work on getting some more information about the final project. Just like I said, send me any questions you have. Thank you so much for your time. I will see you in office hours on Friday.